Have you ever just stopped and wondered how your computer can find one specific piece of information in a massive sea of data, like almost instantly? It really does feel like a magic trick, but I promise you it's not. It's one of the most clever and important data structures in all of computer science. So today, we're going to pull back the curtain on the hash table. I mean, think about it. You start typing a name into your phone, and before you can even blink, the right contact card just pops up. It's not sitting there scanning through every single name from A to Z, right? No way. Something way faster, way smarter is happening behind the scenes. So, how does it actually work? Well, the secret is a concept that sounds, honestly, a little too good to be true. It's called constant time performance, or what programmers call O1. Now, what that means is that whether you have 10 contacts or 10 million contacts, the time it takes to find any single one of them should be pretty much the same. It doesn't get slower as your data grows. And that is the incredible promise of the hash table. Okay, so to really appreciate the genius of the hash table, we first need to look at the most obvious solution and see exactly why it's such a terrible idea. The most straightforward approach, the one you'd probably think of first, is to just create a gigantic array. Think of it like a huge wall of mailboxes. If you want to store a user with ID number 500, you just put them in slot number 500. Super simple, right? Finding them later is instant. You just go directly to slot 500. That's perfect O1 access. So what's the catch? The catch is wasted space. And I mean a spectacular amount of it. You see, you might only have 1,000 users you need to store, but their user IDs could be these gigantic numbers, maybe stretching into the billions. That means you'd have to create an array with billions of empty slots just to hold your 1,000 users. It is wildly impractical and just a colossal waste of memory. And this right here brings us to the elegant solution. If we can't have a dedicated slot for every single possible key, what if we could invent a clever system that maps that huge range of keys into a small, totally manageable number of slots? This is the core idea of hashing. The solution is something called a hash function. Just think of it like a magical converter. You feed it a big, clunky key, like a user ID or even a person's full name, and it spits out this neat, tidy index number that points to a slot in our much, much smaller array. And that smaller array, we call that a hash table. A hash function can be surprisingly simple. A really common one is the modulo operator, which is just a fancy way of saying the remainder after division. Here, we're using it to fit any number into a table that only has 10 slots. And look how it works. It takes these wildly different keys, 2001, 13, 11,456, and assigns each one a unique, predictable slot between 0 and 9. Pretty neat. And this is exactly how we get that O of 1 speed back. It's a simple 3-step dance. You take your key, you run it through the hash function to get an index, and then you jump. You don't search, you jump directly to that spot in the array to get your data. No scanning, no guessing, just a direct jump. But of course, it can't be that simple, right? We've just mapped this huge universe of keys into a tiny number of slots. It's totally inevitable that sooner or later, 2 different keys are going to get mapped to the exact same slot. This is called a collision, and it is the central problem we have to solve with hash tables. So let's make this totally concrete. Our hash table already has the key 157 sitting in slot number 7, because 157 modulo 10 is 7. Now we want to insert a new key, 207. So we run it through our hash function, and 207 modulo 10 is also 7. Now we've got 2 keys trying to live in the same house. And here it is, a direct conflict. Slot 7 is already occupied by 157. The new key, 207, wants to land right there, but it can't. So what do? We can't just overwrite the old data. That would be terrible. We need a strategy. Thankfully, computer scientists have spent decades coming up with some really clever ways to handle these pile-ups. They pretty much fall into 2 main philosophies for resolving collisions. Let's break them down. So the first philosophy is called open addressing. The rule here is super strict. 1 item per slot, period. If your designated slot is already taken, your goal is to find another empty slot somewhere else in the table. The second philosophy, separate chaining, is a lot more flexible. It basically says, hey, it's cool if multiple items hash to this index. We'll just start a list of all of them right here. All right, let's start with open addressing. The most basic method is called linear probing, and it is exactly what it sounds like. If slot 7 is taken, you just probe or check the next one, slot 8. If 8 is taken, you check 9, and you just keep going one by one until you find an empty spot.
But linear probing has a major flaw. It creates something called primary clustering. And I love this analogy for it. Quote, a cluster is like a faint scene at a mall. Initially, the first arrivals come. Later arrivals come because they wonder why everyone was in one place. As the crowd gets bigger, more are attracted. Once a few items land next to each other, they form this big block. Then, any new item that hashes anywhere into that block now has to skip all the way to the end, making the block even longer.
And this clustering just totally wrecks performance. As the table's load factor, which is just how full it is, goes up, the number of checks you have to do skyrockets. When the table is 50% full, a search takes about 1.5 checks on average, but by the time it's just 2/3 full, it's already up to 2 checks, and it gets exponentially worse from there. Suddenly, those instant searches are not so instant anymore. So, to solve this, people invented smarter probing methods. You've got quadratic probing, for instance, which tries to break up clusters by jumping in bigger and bigger steps. First 1 spot away, then 4, then 9. But an even better method is double hashing. It actually uses a second hash function to calculate a unique jump distance for each key. This scatters the data much more effectively, making it the best performing open addressing method out there. Now, let's jump back to that other philosophy, separate chaining. This approach basically says, why bother searching for an empty slot at all? Instead, each of the 10 slots in our table is simply the starting point of a list. When a collision happens at slot 7, we just add the new item to the list that lives at slot 7. It's really simple, and it avoids that whole clustering problem entirely. So with all these different strategies, linear probing, double hashing, separate chaining, how on earth do you choose? Well, it all comes down to understanding the trade-offs. The choice really just depends on your situation. If you need something simple and you can guarantee the table stays mostly empty, yeah, linear probing is fine. If you want the absolute best performance for a table that has a fixed size, double hashing is the way to go. But if you have no idea how many items you'll end up storing, separate chaining is your safest bet, because its performance degrades much more gracefully. But listen, it's crucial to remember that all of this is useless without a good hash function to begin with. The real goal is to minimize collisions in the first place. Some key rules. Make sure every single part of the key influences the final hash value. Don't include redundant data. And here's a little pro tip. Always try to use a prime number for your table size. It just helps scatter the keys more evenly, especially when your data isn't perfectly random. So, there you have it. That's the secret. The hash table isn't magic. It's just this brilliant combination of a simple array and a clever mapping function, with some really smart strategies to handle the inevitable conflicts. It's the engine behind databases, compilers, caches, and so much more. The next time something feels truly instant on your device, you'll know the clever shortcut that's likely making it all happen.